Hello and welcome to Alpha Omega training videos. In this video we are going to simulate the Baffle cut effect on shell and tube heat exchanger using ANSYS Fluent software. Stay with us. At the first step, open your ANSYS Fluent software from the start menu bar, and after a few moments the Fluent launcher window will be opened. In order to import the mesh file, hit the read and select the mesh. Go to the location of your mesh file, select it and hit the open. And as can be seen, the mesh file is added into recent files list. Here we can see the dimension, which is selected 3D by default, and also we have solver options, which the first option is double precision. This option in ANSYS Fluent software is a computational setting that allows for more accurate numerical calculations. This option uses 64 bits to represent numbers compared to the 32 bits used in single precision. The double precision effectively doubles the number of significant figures in the calculations, leading to more accurate results. Also here we have the solver processes under parallel. This option is a feature that allows you to control the number of processes used for the solver. I change it to 12, which is the number of my course. Finally, I hit the start. And it may take a few seconds until the Fluent software is loaded. And as you can see the work done in the console, the mesh file is imported successfully into software. So check the mesh file, and in order to avoid negative volumes, check the minimum volume, which is a positive value. Also we can report the quality of our elements using two parameters. The first is minimum orthogonal quality, while the second one is maximum aspect ratio. The orthogonal quality in ANSYS Fluent is a measure of the cell's deviation from a perfect shape. The range is 0 to 1, where 1 represents a perfect cell. Lower values indicate poor quality, potentially leading to inaccurate results. It's crucial to maintain high orthogonal quality, preferably above 0.1, to ensure accurate and reliable simulations. Also, the aspect ratio refers to the ratio of the longest edge to the shortest edge in a cell. It's an important metric for mesh quality. Fluent can handle high aspect ratio cells, but for better accuracy it's recommended to keep it below 100. However, in boundary layers it can be several thousand. We can also check the geometry of the solution by clicking on Display Mesh option. Select all your surfaces and make sure that the faces is enabled. You can rotate the geometry or zoom out or zoom in. To make the geometry transparent, you can increase the transparency here. And now we can take a look inside of the geometry. You can disable surfaces and look at them one by one. Also, if you want to take a look at the surface elements, you can enable the edges option and then hit the display. And now you can see the tetrahedra type elements on the surface. Also, we can modify the solver options. The solver type is selected as pressure-based. The pressure-based solver in ANSYS Fluent is primarily used for incompressible and mildly compressible flows. The solver uses a pressure correction method to solve the Navier-Stokes equations. The steps involved include guessing the pressure field, solving the momentum equations to obtain a velocity field, and then correcting the pressure field based on the divergence of the velocity field. The process is then iterated until a converged solution is found. This solver is efficient and suitable for a wide variety of flow problems. The velocity formulation is absolute, and in case of time, our solution is steady. In the next tab, we have the models. Double click on models, and here in the task page tab, you can see all models available in ANSYS Fluent software. What we need is to activate the energy equation. And in this viscous section, we can define our turbulence model. Here I select the K epsilon realizable model. This model offers an improvement over the standard K epsilon model by providing superior performance for flows involving rotation, boundary layers under strong adverse pressure gradients, separation, and recirculation. The realizable K epsilon model is based on the transport equations for the turbulence kinetic energy and its dissipation rate. The term realizable means that the model satisfies certain mathematical constraints on the Reynolds stresses consistent with the physics of turbulence. The benefits of using this model include its robustness, economy, and reasonable accuracy for a wide range of turbulent flows. Hit the OK, and the model is defined. In the next section, we have our materials. Double click on it, and here you can see that we have air for fluid and aluminium for our solid dummy. But our fluid in this project is water. So to define water material, click on the fluid, create edit, go to the Fluent database, make sure that the material type is fluid, and go to the end of the list and select water liquid. copy, and here you can see that the water liquid is added. In order to assign the water liquid into our zone, we just need to go to the cell zone condition section. We have just one zone, which is fluid. Select and hit the edit. And here in front of the material name, change the air with water liquid. Hit the apply and close. The next section is boundary conditions. Double click on it, and here you can see all the boundary conditions of the solution. I select this option and I select the last option, which is zone type, and it will classify our boundaries by their type. As you can see, we have one inlet boundary condition, and its type is mass flow inlet. The mass flow rate of water liquid from inlet is 0.5 kg per second. Here in front of the specification method, select K and epsilon, and both the kinetic energy and dissipation rate are 1. Also in thermal tab, we have total temperature of 300 Kelvin. Apply and close the window. Another boundary is default interior, which is the zone of our solution, and there's nothing to modify. The outlet is shell outlet. Its type is pressure outlet. And here in front of the specification method, select the intensity and hydraulic diameter. The backflow turbulent intensity is 5, while its hydraulic diameter is 0.1 meter. And its backflow total temperature for the reverse fluid coming back into the domain is 300 kelvins too. In case of wall boundary conditions, the first boundary is baffle cut, but we want to change its type from wall to interior. So click on it and change the type to interior. Apply and close. The graphics window is out of date, so click on the display mesh and display again, and now it's updated. The next one is baffle walls. Here the wall motion is stationary and the shear condition is set to no slip. In thermal tab, the thermal condition is coupled, and there is a wall thickness of 0.002 meter, and the material name is aluminium. Apply and close. The next boundary is the shadow of baffle walls. It shows that this boundary is inside of the domain, and they are just the same. The next one is shell walls. With a zero heat flux. For the tube walls, I increase the roughness height to 0.0001 meters, and in thermal tab I select the temperature, and the temperature is 450 Kelvin. And the last boundary is wall. And make sure that the heat flux is set to 0 for this boundary condition. Okay, the setup section is completed, and let's go to the solution section. The first section of the solution is methods. Double click on it, and here you can see the pressure velocity coupling schemes. Change the couple to simple. The simple scheme is a numerical procedure used for solving the Navier-Stokes equations which describe the motion of fluid. The scheme is iterative and relies on guessing and sequentially correcting the pressure and velocity field to achieve a converged solution. It's widely used due to its simplicity and efficiency, especially for incompressible and steady-state flows. In a spatial discretization tab, we have the gradient, which is selected as least square cell based option. The least square cell based gradient method for spatial discretization is an approach used to calculate gradient vectors for scalar quantities in the fluid flow. The method works by minimizing the sum of the squared differences between the values of the scalar quantity at the cell centers and the values predicted by the linear approximation of the scalar quantity over the entire cell. This method offers a higher level of accuracy compared to other methods like the Green-Gauss cell-based method, especially for unstructured and non-orthogonal meshes. However, it may require more computational resources due to its complexity. The pressure gradient is standard. The momentum will be solved or discretized with second order upwind. The turbulence, kinetic, and dissipation rate are first order upwind, while the energy is second order. In controls, we have under relaxation factors. The URFs is a numerical technique used to control the convergence of the solution in iterative methods. It's a factor by which the computed change of a variable is scaled down to avoid potential divergence or escalations in the solution process. The range of under relaxation factor in ANSYS Fluent generally varies between 0 and 1. A value close to 0 means that the solution will converge slowly, while the value close to 1 means that the solution will converge faster, but it may lead to instability if the value is too high. Next, we have the report definitions. Report definition is a specification that allows for the automatic calculation and reporting of certain derived quantities during the solution process. If you right click on it, new, surface report for example, and area weighted average, you can define a report from your desired parameter on each of the surfaces, and it will be reported in every iteration. In monitors, if you open it, you can see the residual as the first option. In ANSYS Fluent, residuals represent the imbalance in the solved equations and are used to assess the convergence of the solution. When the solution is perfectly converged, residuals would theoretically be 0. However, in practice, due to numerical errors and approximations, residuals tend to reach a small value and then level off. Here you can see the absolute criteria of the residuals for each of the equations available in solution. Also make sure that the print console and plot options are enabled. To initialize the solution, I double click on the initialization. The initialization is the process of defining initial conditions for the computational domain. This is an essential step in the simulation process as it sets the starting point for the calculation. Standard initialization initializes the whole domain with uniform conditions which are specified by the user. This method is often used when the initial state of the flow field is known. In case of hybrid initialization, on the other hand, is a more advanced method that initializes the flow field based on potential flow solutions. This method is particularly useful when the initial state of the flow field is not well known, as it can help the simulation reach a converged solution more quickly. Select the hybrid initialization and hit the initialize. After 10 iterations, the process will completely done. And let's go to the run calculation section. And here set the number of iterations. For example, we can put 1000 iterations. And finally, click on the calculate, and the solution will start to run. And after a few moments, you can see a new window, which is the residuals for each of the equations. Okay, the calculation is completed and the solution is almost converged. And now we can extract some graphical results. To do that, open the graphics, and here double click on contours. Hit the new surface and let's define a new plane. This is the pressure value in the YZ plane. We can also see the velocity. In order to look at the contours and the geometry at the same time, we need to define a mesh. So double click on it. Go to the scene and enable both the contour and mesh. Hit the save display. But to see the contour correctly, increase the transparency of the mesh. We can also define new planes in ZX plane. And this contour shows the velocity magnitude in ZX direction. Also the static pressure and other parameters like the temperature. Another plane that we can define is in XY plane. At the center of the geometry, which will be 0.3 meter offset from Z direction. Create and close. And this is a good view to save a picture. To do that, click on the save picture, select your format, disable use window resolution, and here you can select your desired resolution, for example 4K, and after selecting the save, the picture will be saved in your desired location. Go to the location you have saved the picture. And there is a high quality image. Okay, other graphical results could be the vectors of velocity. Decrease the number of vectors, you can increase the value of skip. And again, we can define a new scene. Vector and mesh. To extract the path lines, double click on it. Color by, for example, the velocity. And in release from surface, select the shell inlet. Increase the number of steps to, for example, 5,000. And to decrease the number of lines, we can increase the path skip value. And I can increase the line width, for example 5. It's a big value, so I decrease it to, for example, 3. Let's define a new scene. Define and mesh. And this is the final image. Okay, that's it. The simulation is done successfully, and I hope that you have enjoyed this project.